All right, now for something completely different, time domain surveys and what we're doing. So what I wanted to do here was step through the current time domain surveys, what's going on with them, what their focus is, some of the current computing challenges, and then where we're headed in the future. Okay, this works. The forward doesn't work. There we go. Okay, so I divide up surveys into hunters and gatherers. The hunters are the ones that are actually looking for transients that go bump in the night, and the gatherers are the ones who steal the hunters' worthwhile booty. And so we have 4 surveys that are currently running, and they are the Palomar Transient Factory, which has now become iPTF, the I standing for interim, and I imagine there was a hope for trying to get some money from Apple at some point, but that didn't pan out. LaCie Supernova Search, which is sort of a mimic of the Palomar Transient Factory. These are single band filter searches, so they're not obtaining any color information. All they're trying to do is find things that go bump. And then there's PanSTARRS and SkyMapper, and these are surveys which have a longer cadence in general, or a cadence that is not deterministic in some sense. It relies on conditions in the sky. And these surveys are not just after transients, but they are also after a full sky color photometric calibration, a la SDSS. And then we have a couple of gatherers. Pesto is one. This is a spectroscopic survey on the NTT telescope. They get fed by a bunch of people, as well as Supernova Factory telescope on Mauna Kea, which is fed by both PTF and LaCie. So an update on SkyMapper. SkyMapper languished for several years with mechanical vibration issues. It is now turned on and running. It's a 1.3 meter telescope, 6 square degree field of view. Everything's robotic. You can see the size of their imager. Their imager is absolutely beautiful. And it is in Australia, and it is at Sliding Spring. This is Brian Schmidt's project, yes. And so you think of this as Sloan of the South. So they will, I think, provide the first pass all-sky photometric calibration that LSST will use. It also has a Stromgren U-like filter for a lot better stellar work than people have done. But the transient survey has begun, and here is a discovery that they've made. They've had 40 visits over 2,000 square degrees of sky starting in 2013. They're going to ramp up the search through 2014. You can see here are the refs that they've taken. They've got a lot of work to do to fill out the sky. And then a nice detection, and you can see they passed it on to the gatherers, Pesto, and they were able to get a spectroscopic confirmation. So let's show you what a current state-of-the-art pipeline looks like. You have robotic scheduling, et cetera, done at the telescope. The telescope sends the data up through a data transfer node, which then passes it on to your computing facility. Here we're doing it at NERSC. You solve for the astrometry, you do the flat field bias corrections, you grab reference images made from some other source, and then you perform an image subtraction. What we do is we look for 5 sigma candidates on the image subtraction, but you in general take a few images per night, 2 to 3. We're now doing 3 in iPTF. The reason is we want to filter out asteroids which move, and so we also do a nightly stacking of the subtracted images so that we can get deeper than our individual image 5 sigma detection. We get a list of transient candidates which we scan for, and then we have a real bogus system developed by Josh Bloom and his group, which says which ones are viable objects and which ones aren't with some probabilistic determination. And then we compare those to asteroid catalogs, to star catalogs. So one of the first things we do is every night we compute the location of every single known asteroid on the sky so that when we take an image, we can immediately compare it to what things should be in that image and immediately rule them out as interesting astrophysical objects, because I don't find asteroids to be interesting. We also compare to stars. We're not necessarily interested in stars. And so then we get this list. This list gets forked out to a scanning page, but also a robot takes a look at it, and if something passes several thresholds, like in a known galaxy with a known redshift, wasn't seen in the last year to vary, wasn't there last night, and is now, multiple sigma above our threshold, then it sends out an automated message. And now this is on a text message service. All of this takes 40 minutes from the time an image is taken at Palomar to a time a message goes out. And then follow-up is triggered, sometimes automatically, and sometimes we have European collaborators who are browsing through stuff, and if they see anything that didn't get caught by the robot, they pass that on. Okay, so here are a few examples of some science things that I'm going to push through based upon doing this type of rapid turnaround during the night. So this is 2010 MC. Iran Ofek just had this come out in Nature. There's another example of this type of supernova that Pan-STARRS found. And this was our original detection right here. It shot up dramatically. We started getting spectra of the objects at these points. You can see it coming down here. But what we were able to do was go back in the data, and this is our typical threshold for detection, as well as also being an interesting limit. It's the editing limit, 50 times that for a 50 solar mass star. And what happened 20 to 40 days before the supernova became a supernova was that there was some outburst, okay? And you can actually see this outburst in the spectra. You can see these wings on the H-alpha lines. And what had happened was that there was a 2,000 kilometer a second driven outburst about 40 days prior to the supernova explosion. And what they think, the leading candidate for this, is that there are convection motions that are caused by super Eddington fusion luminosity. And now we've detected this in a few events, anywhere from a year to a month before the supernova explosion, that excite gravity waves that propagate towards the surface and shove a layer of the surface out. And then the supernova explodes and runs into it. And that's what we're seeing. What we'd like to do now is be able to trigger on these events, which is why we're doing the coads during the night. And so here you can sort of see a schematic for it. You have about 1/100th of a solar mass of material ejected out a month prior to the outburst at about 2,000 kilometers a second. The supernova explodes, and about 5 days later is ionizing this material, and then it eventually runs into this material, okay? And so that is our view of these supernovae. They're quite interesting. This is the first time any of these have been discovered, and it relies on this cadence, this quick turnaround for the spectroscopy, and then being able to go back in the data and pull things out. Here's another interesting thing. So Fermi goes searching for GRBs, found bunches of them. They're well localized, and they get follow-up. In many, many cases, they have very poorly localized GRBs. To some point, they're 10 to 100 square degrees. And these are the ones that we've decided to do follow-up with iPTF. And so what we do is we get one of these alerts and we hear that the positional uncertainty is large, and then we go plow over this portion of the sky. And here's the first one that we discovered. We got lucky. It turned out to be right on the edge of one of our searches. We weren't able to complete this area that night due to clouds coming in, but this turned out to be a very nice transient that looks very much like the optical afterglow of a GRB, and then it was later confirmed with radio observations. The second one, redshift of 1.87. These were the error circles, the 1 sigma and the 2 sigma. The object was found right there. The key to this was we had to filter out 30,000 other transients before we could hone in on this one. And so what does that mean? That means identifying every single stellar object in here, throwing them out. Identifying every known supernova that had gone off in this portion of the sky and ruling those out. And only looking for things that weren't there the previous night, that it showed up. And of course, GRBs, they decline optically very, very quickly. And so that is the characteristic. In 3 to 4 observations, we see this beautiful drop in the light curve. We've now found the first case of a complete orphan afterglow. Okay? So this was not detected by Fermi. Here are our observations. This was done last month. You can see during the night you had 4 observations that were taken over a handful of hours. You see this dramatic drop right here. The Keck telescope was triggered right over here, and this was the spectrum. You can see iron 2, magnesium 2, Lyman alpha at a redshift of 1.98. The observations were continued by several other observers. It perfectly followed the standard GRB optical afterglow. And eventually, the IPN network went back, looked through their data, and they had a trigger which occurred 20 minutes before, which is, if you fit all of the data that we now have, is exactly when we would have predicted this thing to have gone off. And it occurred 20 minutes before, but with a localization of only 200 square degrees. Yes?
So apparently it was on the wrong side of the Earth, and it wasn't looking at this part of the sky, and I guess you've mentioned Swift, so Swift also. IPN is the interplanetary network, right?
Right.
So there's all these spacecraft that...
Yes, and depending upon the strength, IPN can localize well or not. So this was weak. Matter of fact, I think this was in one of the telescopes, but the strength was such that they wouldn't have seen it. One of the other ones, it wasn't in. Yes. Yeah. Yeah. And so this is the first confirmed case of one of these things. But it required being able to say there's nothing going on, and that the decay of this light curve was analyzed by the software that we have to say this looks like a possible orphan afterglow. And so now the question is, doing follow-up of this, do these look the same as the ones that people trigger on when they're very well localized and say the beam is pointed to you? Does this fit the model that the beam is slightly offline and this is what we're seeing? So this is now the study, and we hope to find several more of these things. Yes, we've been following, well, we followed this for about 4 or 5 days, and then it gets too faint. I think HST, they tried to put in a program for this as well. So, yeah. You can see there's not much of a host galaxy here. This goes to, we searched down to magnitude 23.5, which at this redshift is about 2 magnitudes fainter than the Milky Way. So not great, but fairly deep. Okay, another interesting thing is something that Avishai Galyam has called flash spectroscopy. This paper is coming out in Nature in a couple weeks. So you can see a bunch of non-detections here, and then boom, the supernova goes off, and we were able to get a spectrum the same night at Keck, and then you get this beautiful light curve that's going on. And then here, a zoom in of this area shows you how quickly we were able to get on it. So first P48 image, candidate goes into a database just 45 minutes later. Second image taken, immediately transient alert because it confirms the first observation. And then you can see Swift was triggered, Keck spectrum was taken, swift observation now, just 5 hours after the very first image taken. Follow-up telescopes doing photometric follow-up just a few hours after that. This is what the spectrum looks like. The spectrum here is in black, and what you see it compared to are Wolf-Rayet stars. Okay? What has happened is that you have a wind coming off of this progenitor system, and the supernova explodes and ionizes the gas out there very, very quickly. Heats it up to 100,000, 200,000 degrees. It starts cooling down, emitting photons, and at some point it actually passes through the same temperature regime that this Wolf-Rayet star progenitor was in before, and that's why you see the spectra. And it's not as sensitive to the chemical it's more sensitive to the chemical composition than the exact temperature of the radiation. So you can actually go through and subclassify what type of Wolf-Rayet star was there. Now the supernova ejecta expands, okay? And as you go on a few days later, you can see that the emission from this wind is getting weaker. It's still there, just a little, okay? But it's now being dominated. The overall light is being dominated by the supernova, okay? And then we go on to even later. The supernova has enveloped the Wolf-Rayet wind, and it turns into a type 2b supernova, so hydrogen and strong helium in it, okay? This Avishai has called flash spectroscopy, basically because you flash ionize the progenitor system, this wind around the Wolf-Rayet star, and then the supernova then, as this wind cools, allows you to probe this system. Okay? So, another interesting result. Now, the other thing that these surveys do are build up tremendous statistics on transients, and this is something that's just being exploited. Over 2,000 supernova from iPTF alone. LaCie has found several hundred, Pan-STAR several hundred. 82 papers out of this collaboration. I'm going to say the vast majority of them, 95%, are done on one-off objects or two objects at a time. Some interesting science coming out of looking at the statistics. So this is a combination of the hunters and the gatherers. So the gatherers here are following up a bunch of supernova found by PTF, LaCie, and their own search. And Richard Scalzo just had this paper come out where he did models, so combination of modeling the light curves of the supernova using a very sort of simplistic light curve model for the bolometric luminosity. So it was converting all of the observational data into bolometric light curves, and then modeling both the nickel mass and the total mass of the supernova explosion. And what he wound up getting was that there was a nice correlation between the light curve width and the ejected total mass, and that some fraction of the supernova were sub-Chandrasekhar in mass. There's a systematic associated with this analysis, so you can imagine shifting these up by about 0.15 solar masses, but it still means there's a large chunk of the type 1a supernova which are sub-Chandrasekhar, and that the light curve stretch relationship, which we've been using to calibrate type 1a supernova cosmologically for years, is dominated by the mass. And as a secondary effect, the iron, the nickel production, which leads to iron peak elements, which affect the opacity. So this is quite interesting result based on 20 or so of these supernova. We have 2,000 of those, about 1,600, 1,300 are type 1As. So there's a lot more work to be done in this area, and that, I think, is the next big area in the transient work, is mining in a very controlled statistical sense all of the data that we have from there. So I'll close with a couple of slides on the future. So this is the Palomar Transient Factory. This is something called the Zwicky Transient Factory, which is in the process of being built right now. The cryostat is being built here at LVL. The first 8 chips are put together down at Caltech. with the electronics. It's going to sit over here on the 48-inch. The interesting thing is this is 46 square degrees, so we're going to need something to follow it up in an automated way, and that's called the SED machine, which I'll describe in a second. These are the chips that are going in there. They're 6K by 6K chips. There'll be 16 of them total if the whole focal plane gets filled, so that's 47 square degrees. It will be the largest search engine on Sky until LSST comes on. Survey speed is about 3,800 square degrees per hour. Okay, that's 10 times what we can do in PTF. So this is quite an increase in survey power, and of course objects that you find and objects that you want to follow up. So if we want to get a spectrum of everything, we've got to become more efficient. How do you get more efficient? You automate the spectroscopic follow-up and you remove the human interface. So Tom was talking about this yesterday. How do you negotiate? Well, you own the telescope and then you do all the negotiations with yourself, so there's no sociological problems. But what you do here is you go down to an R of 100, which is just good enough for calibration. You have a very wide wavelength coverage and a 12 by 12 arc-second field of view so that it's trivial to swing over and put the target in there. And then with an efficiency of 40%, any of the transients that PTF or Zwicky Transient Factory finds, this thing will be able to target and classify in 5 minutes. So we'll be able to handle about 50 of these objects a night fairly easily. And so this is how we're going to handle our follow-up problem. The reason I think we need to think about revamping some 4-meter class telescopes in the future is due to LSST. LSST will be generating 15 terabytes of data, so it will be almost an order of magnitude more than the Zwicky Transient Factory in terms of depth, in terms of the number of candidates, etc. There's only one 30-meter telescope to follow it up, okay? So we're going to have to think about this transient follow-up. So there are two ways you can do it. You can say, well, forget about it. I'll never be able to do it. I'll do everything within the LSST data set itself. Or you can come up with a plan to identify the transients that you want to target with criteria that meet your science goals, and then you direct a dedicated smaller telescope that's taking lower resolution spectroscopy to classify the object and tell you, is this object worthy of greater follow-up? And that, I think, is going to be the interesting computational challenge, because if we have advanced LIGO, and it has sort of the same coverage on the sky as the GRVs with poor positioning that we get right now, which are, on the order of 100 square degrees. Okay, LSST can hit this down to 24th magnitude fairly quickly, but instead of 30,000 candidates, there'll be 3 million candidates that they have to sort through and figure out, doing a check of the previous light curves, exactly what everything is and identify the one object out of these millions that is the LIGO gravitational wave trigger. And this is going to be an interesting challenge. And so I'll leave it there. Thanks.